Good day, everyone. And our topic for this meeting is about benzene, alcohol, and phenol. So this is Dr. Erwin or Abrenzi. So for our learning outcomes, first is describe the properties of benzene, alcohol, and phenol. Determine the steps in writing correct chemical formula of benzene, alcohol, and phenol. Name and create chemical structures of benzene, alcohol, and phenol. So this will be the flow of our discussion. First, we are going to discuss benzene, the properties, nomenclature, as well as alcohol and then phenol. So let us begin with benzene. So in 1825, Michael Faraday isolated a hydrocarbon called benzene, which consists of a six-carbon ring with alternating double bonds and has the molecular formula of C6H6. In our last video tutorial, you have learned about hydrocarbon, alkane, alkenes, and alkynes. And as you have learned there, whenever a hydrocarbon consists of double bonds, they are called as alkenes. However, in this example of benzene, there are three alternating double bonds. And because of that, the molecules formed is in a planar structure. So with the chemical formula of C6H6. So this leads to the discovery of benzene. And also, benzene is classified as an aromatic hydrocarbon. So aromatic because it is made up, it has rings, no, it has ring on it. The ring is the double bonds in the structure. So that's why there are skeletal formula or line angle formula that you can be able to find in any other resources wherein it is a hexagonal shape um, with a circle inside. So that is an aromatic compound. So yeah, benzene is an aromatic compound, a ring of six C-carb atoms, each bonded to one H atom. So it is a flat ring structure drawn with ring alternating double bonds, or you can just make it a circle, represented by two structures because the electrons are shared equally among all the C atoms, and are represented by a skeletal formula using a circle in the center instead of the alternating double bonds. So that's why here is an example of the structure of benzene as well as the skeletal formula for benzene ring. Okay, so it depends upon on the questions or depends upon on the problem that they are going to solve later on. But any of the structures are correct. So meaning you can use the first one on the left, the one on the second, the one on the next, and the skeletal formula for benzene ring. So let us talk about monosubstituted benzene. So monosubstituted benzene, meaning to say that these are aromatic compounds containing a benzene ring. A single substituent are named as benzene derivatives. So since the ring contains only one substituent, the ring is not numbered. You have to take note of this because there are two other uh, benzenes. The first one is this one, a disubstituted benzene, and then the polysubstituted benzene. So let us talk first about monosubstituted benzenes. As I've said a while ago, there's only a single substituent. So in the previous video tutorial, you have learned there that there are different substituents, no? The one that causes the bending of the structures of hydrocarbon. Now, in the case of aromatic compounds, there are also substituents. So examples are, it could be an alkyl like methyl, ethyl, propyl, butyl, pentyl, and so on and so forth. It could also be an amino group, like in the and this example you have there NH2, and it could also be an alcohol group or hydroxyl. So that's why there's an OH there. Now going back, there are separate names. We call them as common names. So when a compound did not follow the IUPAC system, perhaps it follows the common name system. Um, though it is confusing for the common name because since it is common name, it is not a standard and it can vary from one place into another. Unlike in a IUPAC system, wherein there are certain rules, just like the one that I presented to you last time on the previous video tutorial, that there are certain steps in writing chemical formula or drawing chemical structure using the IUPAC system. The first one on the left is a toluene. Toluene is a common name, and it is a monosubstituted benzene because there is the benzene structure, the benzene ring, and then there's one substituent. In that case, is methyl. If you would like to name it as in a IUPAC system, the last name should be benzene. Okay, so that's why it is methyl benzene. And again, there's no need to write the carbon position of the alkyl group since there's only one. Okay, so that's why the name is methyl benzene. On the other hand, the second picture, the one on at the center, we have their aniline. Aniline is a common name. Aniline is given whenever there is an attachment of amino in a benzene ring. However, you can name that as amino benzene because that is in a UPAC system. On the third, on the other side, you have here phenol. So there is benzene ring again, but this time the one that is attached is OH. Okay, so it is phenol in common name, but its IUPAC name is hydroxyl or hydroxy benzene. All right, so I hope that you can be able to follow. So here are the other examples of monosubstituted benzene. You have there the toluene, the benzoic acid, phenol, benzaldehyde, acetophenone, benzyl alcohol, and benzyl bromide. So you might encounter this in other subjects. So make sure that you can be able to understand these concepts here so that when you move to the next subjects or next topic, you can be able to relate all the learnings that you have here. So in the case of disubstituted benzene, there are two derivative. There are two substituent. Okay, it could be of the same type of substituent, or it could be a different substituent at all. But the point is that there will only be two substituent. Okay, so you have here on the left side of the screen, this is known as 4-bromo-toluene. So 4-bromo-toluene, why? Because it is a toluene. There is the number one carbon there is the one that is attached to CH3, since that is a toluene. Now, if you are going to count from the carbon, the first carbon, the one that has an attachment of methyl, so you can count there 1 to 4, and you can find their bromine. So instead of writing 4-bromotoluene, you may write here p-bromotoluene. Okay, so where did we get p, m? Yeah, so It came from the position of the carbon, no? In case of bromotoluene, the position is 1, 4. So 1 is the carbon attached to methyl and 4 is bromine. So that's why it is para, meaning it is automatically 1 for bromotoluene. So same thing with other examples like that of chloroaniline, 3 chloroaniline. You may just write there 4 chloroaniline, or another is 1,3 benzene or M-xylene, and 1 chloro for ethylbenzene, p-chloroethylbenzene. So again, do not be confused because we're talking about a mix of the common name and as well as of the IUPAC system. So, but you have to remember that in this example, given na yung the one that is attached to the per substituent. Okay, like for example, in the right side of the screen, you have there 1 chloro for ethylbenzene. So why is it 1 chloro for ethylbenzene? I have to count here. This will be your um, here. It is chlorine first before ethyl. So this will be your first carbon, 1, 2, 3, 4. And then it is a benzene, so that's why it is called as 1-chloro-4-ethylbenzene. However, you can use the symbol like P for para-chloroethylbenzene, and so on and so forth. So let us now talk about polysubstituted benzene or polysubstituted benzene. So in this case, it is poly. So you have to expect that there are 3 or more substituents. They could be of the same kind or it could be of different attachment. So how do we count or how do we name? For example, you have here on the left side, it is a toluene because there is methyl on top. So you have to count closer to those that are attached. In this case, we have a nitro for amino and then chlorine. So if you're going to count from the top one, and if this will be counterclockwise, it will be difficult. So it has to be clockwise. So your second carbon is the one attached to NO2 going to 4 chlorine. So you can be able to name now. So it is 4 chloro, 2 nitrotoluene. On the other hand, we have the second example, the one at the center. You have their phenol. Okay, so there are 3 attachments, other attachments like that bromine. So when you count, it should be same ruling when we name alkane. So the closest, the shortest number combination possible. And we have here 2, 4, 6 tribromo phenol. Okay. On the other hand, on the third example, you have there, it is UPAC name. The first, the first two are a common name. Okay. On the other hand, you have here, it is an UPAC name because you counted and named all the substituent, and then the last name is the word benzene. So you have to remember that. So you have here 1, 2, 3, 4. So in this case, you have to select ethyl since it is closer to bromine. You cannot select bromine and then ethyl going to nitro. Okay, so this is the closest possible combination. So that's why it is 1 ethyl and then to bromine and then 4 nitro. So that's why the name is 2-bromo, 1-ethyl, and 4-nitrobenzene. So let us look into some application or some application of benzene when it comes with that of our daily lives. So toluene is used as a reactant to make drugs, dyes, and explosives such as TNT, known as trinitrotoluene. So that's the chemical formula for TNT. So that is 2,4,6 trinitrotoluene. Okay, so a benzene ring is also found in some amino acid, the building blocks of protein. So, for example, you have their phenylalanine, an amino acid wherein the the benzene can be found. And the benzene ring is found in pain relievers such as aspirin, acetaminophen, and ibuprofen in flavoring such as vanillin. So you have there the chemical structure of ibuprofen with a benzene ring at the middle, vanillin, acetaminophen, and aspirin. So these are all pain reliever drugs that can be able to that is consist of benzene on their structure. Okay, so this time let us talk about the chemical reactions of benzene. So although benzene is resistant to most of the reactions presented thus far for alkenes, it is not completely unreactive. So others are thinking that benzenes are unreactive. However, by far the most characteristic reactions of aromatic compounds is substitution at a ring carbon. So the reaction that we can look into here is substitution. So some groups that can be introduced directly on the ring are the halogen, the bromine, chlorine, um, iodine, in nitro, NO2, sulfonic acid, SO3, alkyl group, it could be methyl to the other number of carbons, and acyl or RCO group. So these are examples of the chemical reactions of benzene. You have here halogenation. In halogenation, here is your benzene plus chlorine. Chlorine is a halogen, so making it as the process halogenation. So it will lead into the formation of chlorobenzene. And of course, there's an acid. Another is nitration, same chemical reaction, but this time the one it is since it is not halogenation, the one that will be added to the benzene is HNO3 with sulfuric acid as a catalyst. And then the NO2 will be attached to the ring plus water. So the term here is nitrobenzene. Another one is sulfonation. So that is the addition of sulfuric acid to benzene that will lead into the formation of benzene sulfonic acid. And the last one is alkylation. In alkylation, it will lead to the formation of an alkyl benzene. First is you have here the benzene plus RX. RX is any alkyl, no? And then you have here um, the R exchange with that of the H for the formation of the alkyl benzene. All right. So I hope that you have learned something about um, benzene in our discussion. So let us now move on to alcohol and phenol. So alcohols contain an OH group connected to a saturated carbon. Meanwhile, phenol contain an OH group connected to a carbon of a benzene ring. So a while ago when we tackled benzene ring, I have shown some examples of reactions wherein phenol is involved. So in our illustration here, the one at the bottom, So you have there an alcohol structure and then phenol, okay, which is an aromatic alcohol. So alcohols are classified as primary, secondary, tertiary, which refers to the carbon bearing the hydroxy group. So in this example, we have here 1 degree carbon. There's only one carbon. Secondary, there are two carbon. And tertiary, there are three carbon that are needed. So what is the nomenclature for alcohol? So again, the same process, no? But this time I am looking into the, in this example, I am looking into two examples. One is in skeletal formula, and the other one is in a condensed formula. So in general, alcohols are named in the same manner as alkenes. Replace the ene with ol. So it will become butanol, ethanol, and so on. So number the carbon chain so that the hydroxyl group gets the lowest number, and number the substituents and write the name listing the substituents in alphabetical order. And for phenol, follow benzene nomenclature and use phenol as the parent name. The carbon-bearing the OH group gets number 1. So from butane to 1-butanol to 2-butanol. So why? So in this example, you have here OH at the end. So it is being assumed that this O is attached here in the first carbon. Okay. So again, our way is that for the UPAC system, you have to look into um, this one, no? You have to look into the position wherein the OH is closer. Is it on the right or is it at the left? So same thing as with 2-butanol, though this is an skeletal model, okay? Skeletal structure or line angle structure. So these are examples: 2-methyl 2-pentanol, 2-methyl because this one. I hope that you are looking into my. Um, let me let me use my pen. Let's see what will be the effect. So you have here the OH is near at the right at the left side. So this will be your first carbon, this will be your second carbon, this will be your third carbon, fourth carbon, and then fifth carbon. Okay. So this is methyl is attached, so there's only one. So 2-methyl, and then OH is found at the second carbon. So 2-pentanol. Okay. Now, on the other hand, I have here, this is an alcohol wherein there is benzene. So if benzene will become your substituent, so there will be a different name. Okay, so you can use phenyl for this for that matter. So that's why the term is, uh, and of course you have to prioritize alcohol over benzene. So alcohol is closer to the one on the right. So this is 1, this is 2, this is 3, and this is 4. So that's why it is 3-pennyl and 2-butanol, right? On the other hand, you have here a phenol with nitrogen, with nitro or amino group. So where are you going to start counting? Of course, here. 1, 2, 3, 4. So your answer is 3, 4 dinitrophenol, right? Okay. So many alcohols are named using non-synthetic nomenclature like benzyl alcohol, allyl alcohol, tert-butyl alcohol, ethylene glycol, and glycerol. So these are the properties of alcohol and phenol. Alcohols and phenols have much higher boiling point than similar alkenes and alkyl halide. So these are the examples. This, um, from water, which is 100 degrees Celsius. For this alkane, you have here the melting molecular weight. Your boiling point is negative 0 degrees Celsius. For alkane with an alkyl halide, you have there 77 degrees Celsius for boiling point. Meanwhile, if it is an alcohol, this is propanol. The boiling point is 116 degrees Celsius. So you can just look here, no, and then trying to analyze that. So alcohols and phenols like water can form hydrogen bonds, non-covalent interaction between a hydrogen atom involved in a polar covalent bond, which the lone pair of a heteroatom, which is also involved in a polar covalent bond. So these are the structure for that. Okay, so hydrogen bonds are broken when the alcohol reaches its BP, which requires additional energy. Right. So these are the reactions of alcohols and phenol. So we have here dehydration of alcohol to produce alkene. So dehydration because you will be able to get water from the structure. Okay, so for example, you have here water and another water here at the bottom. Okay, and then the alcohol underwent uh, chemical reaction and then there. So that is a dehydration reaction because you have taken a certain amount of water, no, from the structure. Okay, so same thing as with the second example. So another one is dehydration of alcohols to produce alkene. A while ago, it is to also to produce alkene. So you have here CH3, CH2, CH, CH3OH. How do you name this one? So this is 1, 2, 3, 4. So this is 2 butanol. Okay, so if there is more than one possible possible product of a dehydration reaction, the major product can be predicted from St. rule. When an alkene is produced in an elimination reaction, the major output is the one with the more highly substituted double bonds. Right? All right. So that ends my discussion about benzene, alcohol, and phenol. So these are the references if you would like to go back to the source. And thank you so much all for watching. See you again by next time. Keep safe.